Hello, so this is a recorded lecture, I suppose, all about the exam for PHY 101 Relativity in 2013 to 2014. That's last year's exam. And this is a spoiler warning that this video will actually go through the exam paper. So if you want to use that exam paper as practice, you should please go away and do the paper without having watched this video. And obviously if you want to know how I would go about these problems, then watch afterwards. So let's get started. Question 4 on PHY 101A from last year is where the relativity section started, and this was a compulsory question. So we have a proton and an electron. They both have kinetic energies of 200 MeV in the laboratory frame of reference. And so part A is the electron non-relativistic, mildly relativistic, or highly relativistic? Now if you remember, in the course I made some hard definitions. I said that non-relativistic particles had V of less than 0.3 C. Mildly relativistic had 0.3 C less than V less than 0.99 C, and highly relativistic had V greater than 0.99 C, where obviously C is the speed of light, 3 times 10 to the 8 meters a second. Now you can convert these V's into betas and gammas. So beta is just defined as V over C, so in that case it's 0.3. So if beta is less than 0.3, you call it non-relativistic. Gamma, which is 1 over the square root of 1 minus V squared over C squared, which equals 1 over the square root of 1 minus beta squared. Okay, that gamma for a beta of 0.3, turns out that gamma is less than 1.05. So if you discover that gamma is less than 1.05, you're in the non-relativistic regime. Similarly for the mildly relativistic, 0.3 C is equivalent to beta of 0.3. So the criterion for mildly relativistic is 0.3 is less than beta, is less than 0.99. And correspondingly for gamma, we have 1.05 is less than gamma is less than 7. Okay? So in the highly relativistic regime, we have beta greater than 0.99 or gamma is greater than 7. Now when you're making approximations, it's worth remembering that I'm perfectly happy with non-relativistic particles being treated as if gamma was approximately 1. So if you set gamma equals to 1, I won't mind. Mildly relativistic particles, beta and gamma, are both significantly different from their non-relativistic values. So beta is significantly greater than 0, and in fact it's greater than 0.3, and it's less than 0.99, and gamma is between 1.05 and 7. So in the mildly relativistic regime you can't approximate either beta or gamma to anything that saves the algebra. Highly relativistic case, I'm happy for you to take beta equals 1. But do remember that that doesn't mean that 1 minus beta equals 0. You'll see how that affects this problem in a minute. So let's go to the first part with the electron. So we know the total energy, the kinetic energy of the electron, which equals gamma minus 1 times the mass of the electron times c squared. Right? And so I'm told that the kinetic energy is 200 mega electron volts. Right? Now we know that the mass of the electron, Me, is equal to 0.51 MeV upon c squared. And so that will allow us to calculate gamma. So let's do the electron first. The kinetic energy equals gamma minus 1 times the electron rest energy, so that gamma equals 1 plus the ratio of the kinetic energy to the electron rest energy. But in this case, that ratio is 200 MeV over 0.51 MeV, which is quite clearly approximately 400. So this number T, the kinetic energy, is about 400, and therefore, so gamma is about 400, which is clearly much bigger than 7. So the electron is highly relativistic. And your one sentence justification of this would be that the criteria for a particle to be highly relativistic is that gamma is bigger than 7. In this case, it's about 400, which is significantly bigger than 7. Therefore, it's a highly relativistic particle. So we'll do the proton next. The proton has a very different rest energy or rest mass, and that means that things are not going to be quite the same. So gamma equals 1 plus the kinetic energy over m proton c squared, which equals 1 plus 200 MeV over 938 MeV. Now this number is about a quarter, so gamma is approximately 1.25, which is bigger than 1.05 but less than 7. So that implies that our proton is mildly relativistic. So the next part of this problem involves trying to figure out exactly what beta and 1 minus beta are for the proton and the electron. So the proton is actually the easier case from the point of view of a beginner. Because it's mildly relativistic, to convert beta to gamma, or the reverse, you simply use the definition of gamma, which is 1 over the square root of 1 minus V over C all squared, or 1 minus beta squared. And we know that gamma is 1 plus 200 MeV over 938 MeV. Let's do that calculation precisely. 1 plus 200 divided by 938 is 1.21. So that we have, starting with this definition of gamma, we have that gamma squared equals 1 over 1 minus beta squared, so that 1 minus beta squared equals 1 upon gamma squared, or beta squared is 1 minus 1 upon gamma squared, or that beta equals the square root of 1 minus 1 upon gamma squared. So if gamma is this, gamma is 1.21, 1 over gamma squared equals 1 divided by 1.21 squared, which is 0.683. We'll just do 0.68. And so we have beta equals the square root of 1 minus 0.68, which is the square root of 0.32, which is 0.57. So that's beta. Now because beta is nicely between 0 and 1, it's not very close to 0 or very close to 1. 1 minus beta is just 1 minus 0.57, which is 0.43. And so that is the end of the proton. So it's very simply a matter of substitution into this formula for gamma in terms of beta. For the electron, things get a little bit more interesting. The electron's highly relativistic. So we calculate its gamma. Gamma equals 1 plus the kinetic energy over the rest energy of the electron, which is 1 plus 200 MeV over 0.51 MeV, which equals 393, which is much bigger than 7. So I can perfectly happy for you to write beta equals 1. If you want, you can write beta's approximately 1, you'll still get the marks. It's a highly relativistic particle, you get marks for recognizing that. No need to figure out that it's 0.99999, whatever it is. Who cares about that many significant figures anyway? You hardly ever need that many significant figures. In fact, just a general point for the exam, if you find yourself writing an answer with 7 or 8 decimals, you're going to lose credit for that. People don't like people to use too many significant digits. Unless you've been asked to quote to 6 or 7 significant figures, don't do it, because you will actually lose marks. Okay, what about 1 minus beta? Now 1 minus beta is not equal to 0, as I said before. The way you calculate 1 minus beta is you can do it 2 ways. You might remember in the lecture course I showed you that for highly relativistic particles, gamma is approximately the square root of c upon 2 epsilon. Now epsilon is the difference between the speed of light and the velocity of the particle, which equals c times 1 minus beta. And so actually gamma is approximately the square root of c over 2 c times 1 minus beta, which equals the square, so gamma equals the square root of 1 upon 2 1 minus beta. And you know what gamma is, so you can plug into that formula to get 1 minus beta. However, you don't have to start by remembering this formula. You can just start from gamma equals 1 over the square root of 1 minus beta squared. And all you have to do is to recognize that you can write 1 minus beta squared as the product of 1 minus beta and 1 plus beta. But 1 plus beta is approximately 2. Okay? And so we have gamma equals 1 over the square root of 2 1 minus beta. And oh look, it's exactly the same result as we got by going from this memorized formula. And so this is all you need. And so let's rub out the memorized formula, because I always prefer to do things from first principles rather than remembering stuff, partly because I have a dismal memory. Take the square of the formula, we get gamma squared equals 1 upon 2 1 minus beta. So that 1 minus beta equals 1 upon 2 gamma squared. Now you can see that this is going to be a small number because gamma is 393, but it's not going to be 0. Okay, so this formula is going to give you a way of getting 1 minus beta without messing up with your calculator and running into significant digit problems, which is what would happen if you just substituted directly into gamma as 1 over the square root of 1 minus beta squared. You'd end up with trouble with significant digits. So in this case, 1 minus beta equals 1 upon 2 times 393 squared, which equals 1 divided by 2 divided by 393 squared, which is 3.2 times 10 to the minus 6. So that is the ratio of the difference between the electron velocity and the speed of light to the speed of light. So if we want to know how much less than the speed of light the particle is going, we simply multiply that fraction, 3.2 times 10 to the minus 6, by 3 times 10 to the 8 meters a second to get 971 meters a second, which is just a little bit less than a kilometer a second. Now when you think about it, that's a tiny discrepancy compared to the speed of light, which is 3 times 10 to the 5 kilometers a second. And so that tells you that this particle is moving very close to the speed of light, which is not surprising because it's highly relativistic. Okay, we'll go on to the next bit of the problem in the next clip.